Hi guys, welcome to the first video in the series on optimization under math studies. In this video we shall tackle the easiest questions in the past papers and the ones that do not have any geometry involved in the question, because most optimization problems involve some geometric manipulation. So we're going to start with the questions that do not need any geometry background as an introduction to the coming more challenging optimization problems. I shall tackle the three questions on the screen in front of you, and I shall begin the first question shortly. So the first question that we shall tackle came in paper 1, May 2015, time zone 2, question 15. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So we are told that a building company has many rectangular construction sites of varying widths along a road. The area A of each site is given by this function right there. So this is the area where x is the width of the site in meters and x lies within this domain 20 to 180. Site S has a width of 20. Write down the area of S. So I shall simply plug 20 into this formula instead of x, and this shall give me 3,600 meter squared. In question B, I'm told site T has the same area as site S, but a different width. Find the width of T. So I'm told that the area is the same. So A has the same value. So area equals 3,600, which I obtained from my answer to the previous question. I now need to find the value of x. So I shall simply plug 3,600 into this equation and equate to x times 200 minus x, as you can see in purple, and I shall expand and solve, getting these two possible values of x. Of course, 20 is the value that was given to me in question A, so the other width that yields the same area shall be 180. So again, what I've done here is simply plug the answer to A, which required the area, plug the number I found into this value right there, and find the second value of x that gives me the same area. In question C, I'm told when the width of the construction site is b meters, the site has a maximum area. Write down the value of b. So this is the core of this topic, the idea of a maximum area or a minimum area and so on. So the maximum area occurs when a dash equals 0, and this is consistent with our knowledge of stationary points and so on. The maximum value of y occurs at the point where y dash equals 0. Hence, similarly for A, the maximum area shall occur when a dash equals 0. So I just need to obtain a dash and equate it to 0. So since a equals 200x minus x squared, which is the expansion of this function, this is the same as the question. Now, a dash shall be the derivative of a, so the green expression right there is the derivative of the purple expression, and I shall equate this green expression to 0 and find x. Hence, x, or rather b, equals 100. This is the value of x that makes a dash equal to 0, and hence makes a equal to its maximum value. In double I, I'm required to write down the maximum area. So I shall simply plug the value of x that I found in I into the original equation for the area. So, since we found x to be equal to 100, I shall plug 100 into the function or the formula for the area, and this gives me 10,000. So 10,000 is the maximum value of the area that I could possibly get. Finally, in question D, I'm required to write down the value of m and of n, which are the limits of the area. So the minimum value of the area and the maximum value of the area. So we already know that the maximum value of the area is 10,000, which we found in CII. Hence, n equals 10,000. This is simple enough. So what about the minimum area? The minimum area has been found at the very beginning of the question, in question A, because I know that the values of x extend from 20 to 180, and that the maximum occurs when x equals 100. So where will the minimum occur? So obviously the maximum occurs somewhere in the middle of this domain. So this suggests that the minimum values occur at the ends of the domain. So I can try to plug 20 or 180 into the formula. And we already know from A and from B that both 20 and 180 give me an area of 3,600. So this is a quadratic equation, a parabola, with a maximum value at x equals 100 and minimum values at x equals 20 and x equals 180. What is the minimum value? The minimum value was already obtained in A, which is 3,600. If this is all confusing for you, what you can do is you can sketch the equation. You can sketch the equation of A and find where the minimum value is. However, this is a one-mark question, so if you understand the concept behind it, it will be just easier to write the values down. So this concludes our first question. Take a minute to write the answers down if you will, and I shall begin the second question shortly. So the second question came in paper 1, May 2016, time zone 1, question 15. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So we are told that a company sells fruit juices in cylindrical cans, each of which has a volume of 340 centimeters cubed. The surface area of a can is A centimeters squared and is given by this formula right there, where R is the radius of the can in centimeters. To reduce the cost of a can, its surface area must be minimized. In A, you are required to find dA by dR, which is simply the derivative of this expression. So I shall first rewrite the expression. This is the formula given in the question. I have rewritten it to look like this, where I've taken the R to the numerator and I've raised it to the power of -1. So these two expressions in blue are similar, of course. This will help me in differentiating the function. Now, the first component of the expression, 2 pi r squared, becomes 4 pi r, and the second component becomes -680 r to the power of -2. In question B, I am told calculate the value of r that minimizes the surface area of a can. So the minimum area of the can shall occur when A dash equals 0, as we explained in the previous video. So I need to find the value of r that makes A dash equal to 0, and this is either solved algebraically, as you can see here, or if the algebraic approach is problematic for you, you can always use the GDC as follows. So I've written the function down on the GDC. I've taken some time to adjust my window, and this is the problem with the GDC method, which is that sometimes the function is difficult to adjust in terms of the window. It might take you some time. So I played around with the x minimum, x maximum, y minimum, and y maximum until I got this drawing right there. I want to see, or I want to find the value of x that makes this function 0. So I shall press second, calc 0, left bound, right bound. So I'm looking for the x-intercept, and it is somewhere there. So the calculator tells me that y equals 0 when x equals 3.78, and this is the value that I'm looking for. R equals 3.78. I would rather you do this using the manual approach because it will take you some time to adjust the window and to try to understand what the function looks like on the GDC. So the manual approach is simply to set the expression equal to 0, and I've taken r power negative 2 to the denominator, and it has become r squared. So this is a dash. Next, I've taken this second fraction right there, and I've transferred it to the right hand side. Now it's positive, of course. Next, I multiplied both sides by r squared to get rid of this denominator. So I got 4 pi r cubed equals 680. Next, I divided 4 pi from both sides. So I got r cubed equals 680 over 4 pi. And this final step right there is doable using the GDC. You just get the cubic root of this expression, and this is easy enough to do. So I would recommend that you try to take a second look at this method, because this pattern is repeated a lot in optimization problems. We will meet a lot of problems that require similar algebra in order to isolate the variable and find the value. So you've taken a look at both methods, the algebra method and the GDC method of finding R. You can choose whichever one you like. This concludes our second question, and in a minute I shall begin question 3. Take a minute to write this down if you will. So question 3 came in paper 2, November 2004, question 8, IV. Take a minute and attempt to solve, and the answer shall follow through shortly. So we are told that the cost of producing a mathematics textbook is $15 US, and it is then sold for X dollars. In question A, we are required to find an expression for the profit made on each book sold. So profit equals selling price minus cost. Hence, the profit here is equal to X minus 15. In question B, we are told that a total of 100,000 minus 4,000 X books is sold. Show that the profit made on all the books sold is this expression. So I want the total profit, which of course shall equal the profit made on one book multiplied by the number of books that I shall sell. So I shall simply multiply the expression I obtained in A, which is the profit per book, by the number of books which I've been given right there, getting this expression, and I shall expand using regular algebra, getting these 4 terms in purple right there. I've added the 2 similar terms, which are 100,000x and 60,000x, and this gave me 160,000x, and the second and third terms remain as they are, and I hence obtained the expression in red, which is exactly the same as the one I was asked to obtain in the question. In CI, I'm required to find dp by dx, which is the derivative of p. This is simple enough. 160,000x just becomes 160,000. Negative 4,000x squared becomes negative 8,000x, because I've multiplied the old power by the number, getting 8,000, and I've reduced the power by 1, so I have x power 1. and the third term is just a constant, so it vanishes during differentiation. In CII, I'm told hence calculate the value of x to make a maximum profit. Again, we said before, maximum profit means p dash equals 0 or dp by dx equals 0. So I'm just going to equate my green expression right there to 0 and find the value of x, which turns out to be 20. In D, I'm told calculate the number of books sold to make this maximum profit, and all you need to do here is simply plug the 20 into the equation for number of books sold, or rather the expression for number of books sold, which is this expression right there. I shall simply plug 20 instead of x, obtaining this blue expression, and some easy simplification, and you get a final answer of 20,000 books. So this concludes what I hope has been an easy question and an easy video to watch in general. These are introductory problems in the field of optimization. I shall next progress to videos dealing with geometry and then dealing with more challenging problems. I hope you have found this video useful.